I wanted to take a minute to finish up Chapter 8 today, and then we'll move on to Chapter 9. Just a quick note, I sent out an email this morning. Next homework assignment is due on Monday. Is that main light making it really hard to see the screen? Is that okay? Is that okay? Okay. So the next homework assignment is due on Monday. And if you have not submitted your extra credit and would like to, please do so by noon today. It'll be the cutoff. And I have your homework 6s to give back to you. I'll do that at the end. And there was one that didn't have a name on it, so if you submitted it but don't have a grade on Carmen, please let me know. And it's maybe a good time to remind you that please be checking your grades. My grader is not perfect about entering grades. So over the course of the class, if there's a homework assignment you turned in that you don't have a grade for, please let me know. We'll get that entered in. Any other questions or comments before we get started? No? Okay. So again, I wanted to wrap up this last example from Chapter 8. We're talking about doing a hypothesis test here for a proportion, and I think we're on the very last page of your notes here. So on Wednesday we did part A of this problem, which was on the bottom of the previous page. We're looking at body mass index for female workers here, and we were looking at do we have evidence to conclude that more than 20% of female workers have a body mass index of over 30, and so we conducted the appropriate hypothesis test, and I think the conclusion was that we failed to reject the null hypothesis, so we couldn't, based on the evidence that we had, we were unable to reject. Okay, so then these next two parts are similar to, I think, maybe the last homework assignment, or last homework problem, or one of those later ones anyway. And so if you're stuck on those, this will be a good review for that. Okay, so now what is the probability of not concluding that more than 20% of female workers are obese when the actual percentage of obese female workers is 25%? Okay, so this is I was working with some people in the tutor room on Wednesday, and it's these errors they can really make your brain hurt. So let's figure out what we're asking for here. So we want the probability of something given that the actual percentage of obese female workers is 0.25. So I want the probability of not concluding that more than 20% of female workers are obese. So what is that in terms of my hypotheses here? Yes, exactly. So that's concluding. So not concluding that more than 20%. So that means I've sort of gone with the fact that p is less than or equal to 0.2. And so which one of my hypotheses is that in support of? That's supporting the null hypothesis, right? So so not concluding that more than 20% of female workers are obese, that means the probability that I fail to reject the null hypothesis. Okay. So we want to find a probability of a type 2 error here, right? We're failing to reject the null hypothesis when, in fact, the null hypothesis is false. So we want the probability that we fail to reject given that p equals 0.25. And if p equals 0.25, just to note that means that the null hypothesis is false. So if p really equals 0.25, then my null hypothesis is false. So I should have rejected the null hypothesis, but I didn't. So what's the probability that happens when p is really equal to 0.25? Okay, so we want the probability of a type 2 error here. Okay, so we have a significance level of alpha equals 0.05, and the alternative hypothesis HA is a right-sided hypothesis. So I only care about greater than. I don't care about less than or not equal to. So again, I want to. So if I draw my standard normal curve down here, centered at 0, what area under this curve, where am I going to reject, where's my rejection region for my test statistic on this curve? If HA is, P is bigger than 0.2. So where would your p-value, if you calculate a test statistic, and where would you look to find your p-value? The tail, yes, exactly. So, and which one?
The right tail.
The right tail. Why do you say the right tail?
Because it's greater than 0.2.
Yeah. So our alternative says greater than, so we want to look for values that are sort of extreme in the large end of the spectrum. So we want to, if areas of our test statistic that are large on the positive side are going to be values that cause us to reject. So if this is, if we can find what number there to gives us a 0.05 probability up there, getting a test statistic that's larger than that value will cause us to reject. Getting a test statistic that's smaller than that will cause us to fail to reject. So if my test statistic is up here, I reject. If it's from here over, it's from here this way, I fail to reject. Okay? So just kind of thinking before I actually look at my data, if my test statistic is bigger than that question mark value, I'm going to reject the null hypothesis because that will give me a p-value smaller than 0.05 and vice versa. So if my test statistic is smaller than that value, I will fail to reject because that will mean my p-value is larger than 0.05. Okay, is that okay what we're doing here? Okay. So what is this value here is the question. So that's the probability that a standard normal random variable is bigger than whatever that number is equals 0.05. Right, I want to find sort of like that backwards probability calculation that we've been doing a lot here. And if you go to the table, you can figure out that this is 1.64. Okay. So 1.64 is sort of our important number here. It's sort of our cutoff between, for our test statistic, it's our cutoff between rejecting and failing to reject. Is that okay with everybody? This is a tricky thing, I think, to keep straight. Okay. So what that means here is that we will reject the null hypothesis if our test statistic is bigger than 1.64, and we will fail to reject if our test statistic, which is a z here, is less than or equal to 1.64. Because this means my p-value will be less than 0.05, and here my p-value will be greater than 0.05. Okay. So I want to know the probability that I fail to reject the null hypothesis given that p really is 0.25. So what value of my test statistic will I reject under our current test? So I will fail to reject when z, which is my test statistic, which is p hat minus p naught, divided by the square root of of p naught times 1 minus p naught over n. And so here I'm solving for p hat. I want to figure out what value will cause me to reject. My hypothesized value is from the null hypothesis is 0.2. 0.2 times 0.8 divided by 541 is my sample size. So I'm going to fail to reject when this is less than or equal to 1.64. Okay? Or if I solve this in terms of p hat, I'll fail to reject when p hat is less than 0.2 plus 1.64 which is 0.228. Okay, so I'm just kind of going back in terms of my original, I'm talking about the sample proportion here, so what value of my sample proportion will cause me to fail to reject. So I'll fail to reject if my sample proportion is less than 0.228. Okay, and so maybe now's a good time to quick jump back here. So the actual proportion, the actual sample proportion I got was p hat was 0.222. Okay, and that is indeed less than 0.228. Right, so I'll fail to reject if my p hat is less than 0.228, which is what we have here, and indeed we did fail to reject. So just kind of thinking about how that worked here. Okay, so then to actually calculate my type 2 error here, so the probability that I failed to reject, which means that p hat is less than or equal to 0.228, given that the true proportion is really 0.25. This is kind of just the usual thing. So this is the probability that a standard, well, so if the true proportion really is 0.25, then p hat minus 0.25 over 0.25 times 0.75. Oh wow, that is hard to see at the top there. So well, I'll just go over here. So if p really is equal to 0.25, then z, which is p hat minus 0.25 over square root of 0.25 times 0.75 is distributed as a normal random variable, right? So if the true proportion is 0.25, then if I standardize in this way, I'll get a standard normal there. Okay, so this probability that I want is what do I want here? So I want the probability that a z is less than or equal to 0.228 minus 0.25 over square root 0.25 times 0.75, 541. So probability that z is less than or equal to negative 1.18. You go to your table, you can find that this is 0.1190. Okay, so the probability that I failed to reject if the true proportion really is 0.25, about 12% here. Okay, so this is pretty good anyway, right? So this is the probability that I make an error, right? And that probability it's not that small. It could be smaller, but the reason we're doing these calculations is it helps us to know kind of if the alternative hypothesis really is true. So if the true proportion really is in above 0.2, what are the chances that I make this kind of a mistake? And so again, that probability is about 12%. It's not that small, but it's not that big either. So this is a way to help you sort of feel confident about the test that you're doing here. Is it going to help me detect? Am I going to be able to reject the null hypothesis when I should? Okay. Yeah, Kyle.
So if there's ever a question about power or like probability of type 2 error, does pretty much have to have like some kind of this is what the real mean was?
Yes. Yeah. Yep. So anytime, right? The question was anytime you have a question about type 2 error or power, it'll be for a particular value of the parameter. So if the true mean really is whatever, or if the true proportion is really 0.25 or whatever, you're always making that calculation under a particular alternative hypothesis. Yeah, good question. Yeah.
So just to check my understanding, so is what we're really doing then, if we have like a true mean, we're saying that is like the mean of the normal distribution, and we're finding
Mm-hmm.
percentage of what the likelihood of finding that particular value is.
Yeah.
in the distribution.
Yeah.
That's
Yeah. Right. So you're kind of saying, if the real mean had been 0.25, sort of, yeah. How likely is what I got in some sense? So how likely am I going to, am I going to make the correct decision? Kind of is the idea. Okay. Okay. Well, we're going to take this problem just one step further. So,
conclusion back there, like we did on the other one.
oh,
Is that required?
no. So we don't need to give a conclusion here. Well, you could just say, so the probability of a type 2 error equals 0.1190. If you want to formalize that, yeah. So we're just asking for the question. We're just asking for a probability, and so if we just give a probability, that'll be good. Yep. Okay. So this I ask you to do this on your homework as well. So what sample size would be necessary for that answer in part B to be 0.1? So all the way through this previous calculation here. I had a particular sample size, right? I plugged in what my actual sample size was. I did that over here too. So now what if I leave my sample size as sort of if I kind of leave that open to see what I need, I can change my sample size to change this probability is the point here. So what sample size would I need for this answer to have been just a little bit smaller? So again remembering that I'm going to fail to reject. Remember if p hat minus 0.2 over n was less than 1.64, same as saying p hat, I would fail to reject if that's less than 0.2 plus 1.64. So leaving n in there as an unknown. Okay. And if I want the probability that I failed to reject, so if I want the probability, if I want that probability to be 0.1, so I want to figure out what number that is such that this probability is 0.1, and that's the same kind of the same setup as we had here. Probability that z was less than, we're looking at that because we failed to reject when we have a less than. And you can find this number to be negative 1.28. Okay, so if my test statistic is less than negative 0.128, that probability will be 0.1. Okay? And again, here remember that z is a p hat here minus 0.25. This is under the alternative being that the probability is really 0.25. But we'll leave an n in there for now. Okay, so kind of doing the same thing that we did before. Okay, so we want to now just set our test statistic equal to negative 1.28, or figure out our rule that way. So I think I jump over to a new slide here. So what I want to do is set negative 1.28 equal to p hat minus 0.25 divided by n. Okay, but then the p hat value that I actually care about here is this thing up here. So again, the p hat that I'm concerned about will depend on my sample size, will depend on n. So we can take that and we can plug that into this next formula here. So what we can do is plug in the endpoint there. So 0.2 plus 1.64 times 0.8 divided by n minus 0.25 Okay. So really, I'm just doing the same calculation we did in part B, just leaving n in there as an unknown. So anyway, then you can solve. This is just an equation of n. It's kind of a messy equation, but if you solve that for n, you'll get that n equal to 585.6. And so again, we can't have partial observations here, so we round up. And take n equal to 586. So if my sample size had been slightly larger, my sample size, remember before it was 541, my sample size had been a little bit larger, the probability of a type 2 error would have been a little smaller. So this is kind of a key idea. Larger sample size implies a smaller probability of a type 2 error. Okay, so maybe a little bit larger conceptually. Does that seem like a problem? I can, if my sample size is larger, I make I have smaller and smaller probability of a type 2 error. So that could be bad, right? I could just take my sample size to be twice that, 1,000, 2,000. The bigger my sample size, the smaller probability of type 2 error I will have. So there's some issues underlying what these tests can do if your sample size is really big. But that's just a point to keep in mind. If your sample size is larger, you're less likely to make a type 2 error. Okay. Any questions or comments on this? Yes, Pete.
Is there a limit? Or is it just arbitrary depending on what your sample is for?
Is there a limit on your sample size, you mean? Oh, yeah. So is there a limit? I guess it's really just... I mean that the limit would depend on how big your population, I guess is in some sense.
I mean, is it a certain percentage of your population? Like if you have 1,000 people, you don't want your sample size to be 950 or whatever, right?
Yeah. So if your sample size is only 1,000, if your population size is 1,000, you don't want to sample like 900 people. Yeah. There are some issues. There are some issues with that we don't really talk about in here. But sort of a good sample size is sort of in sort of a sweet spot. You want it to be large enough so that these results kick in, that we can use these tests. But if it's too big, then you can have some problems start to happen as well. So I don't know that there's not necessarily a rule of thumb as a certain percentage that you have there or anything like that. But yeah. Yeah, Kevin.
Are you saying if your sample size is too big, you have a probability of ignoring something that is more likely to happen? Is that the idea with it?
So if your sample size is bigger, you're more likely to ignore something that is.
It's actually more likely than you think.
It's actually more likely than. So what this again type 2 error says that that's the probability that we make the wrong decision by failing to reject the null hypothesis. So in sort of vice versa, you're kind of saying you're more and more likely that you will reject the null hypothesis. It's less likely that you'll fail to reject, so it's more likely that you will reject the null hypothesis. So it's sort of like if your sample size is big enough, you can reject any hypothesis that you want. So that's kind of the issue, that you don't want your sample size to be too large because you might detect something that's not actually there. Yeah. A little more conceptual there, I guess. Okay. Okay. Well, before we move on to Chapter 9, I wanted to quickly go through an example. Before we wrap this up. So we're moving on to a new chapter here in just a second, but we're going to be doing more hypothesis tests, and we'll do it for the rest of the semester. So this is sort of confidence intervals and hypothesis tests, I guarantee you'll see this stuff later in your academic career, sort of regardless. So just wanted to I don't think I've formally said this well enough, but again, it's always important to interpret the conclusion that you make, reject or fail to reject. So if you reject the null hypothesis, the correct way to interpret that is we're saying I do have enough evidence, or there is sufficient evidence to conclude, and then you can say the alternative hypothesis. So whatever your alternative hypothesis is in a particular setting, if you reject the null, you say I do have evidence to conclude the alternative. And if you fail to reject the null hypothesis, again, it's kind of getting back to this sort of ticky-tacky language that we're using, but again, you're not concluding that the null hypothesis is true. You're just saying I don't have enough evidence to reject it. So what you say, there's not sufficient evidence to conclude that whatever the alternative says. So you're always giving your conclusions in terms of the alternative hypothesis. And that maybe makes sense because, again, remember the alternative is kind of usually the question that we're trying to answer there. So either there is sufficient evidence to conclude the alternative hypothesis, or there is not sufficient evidence to conclude. So on the final exam, I'll be fairly picky about your interpretations to make sure that you have these down. Okay. Before we move on, I wanted to bring in one of these extra credit data sets that somebody submitted, just to kind of show you how we can use this stuff in real life. So this is one of the first extra credit data sets I got. I'm not sure if submitter is in here, but the data that they submitted was on vehicle ownership in countries around the world. So the data that we have is a vehicles per 1,000 people, and we have this data on 87 countries. And this data might be interesting because it might sort of indicate the wealth of the country, but it's sort of a more robust measurement. So it's not, individual people aren't driving this number up. It's a rate per 1,000. And we could maybe think about questions like, is there a middle class? Can people of all economic classes afford a car? And this type of thing. So can anybody think of a question that we might want to answer based on this data, or how we might use this?
You get that data.
What's that?
How do you get that data?
How do you get that data? You go to that website. How do they collect the data?
Well,
Yeah, yeah. We have to. Well, I guess we have to assume that we have correct data here. Yeah, Matt.
You can see the extent of the recession that's going on around the world. See how bad it really is, in terms of the middle class and diminishing.
Okay. So how would you measure, if we want to say something about the middle class? How might you measure that? Yeah, I mean that's a great question. I would just take it a step further.
Maybe trying to think in terms of a confidence interval. You gotta be able to find the mean of that data set, and then depending on the country, you might be able to find whether that country is better off than the rest, or something like that.
Yeah, absolutely. So we could sort of do an overall comparison and then look how individual countries compare to that range. Yeah, absolutely. Anybody else have a comment or a question they could think of here for this? Well, so I actually, the question I thought was actually almost exactly the same as what Matt just said. So the question that I thought might be interesting to look at is sort of how does the rate of vehicle ownership in the U.S. compare to vehicle ownership around the world? And I don't know. This is not going to make any economic statement or anything like that. But I was just sort of, Americans drive a lot, and the rest of the world doesn't drive quite as much. So I wanted to kind of think about that. So the question that I said that I might want to test is that maybe are Americans at least twice as likely to own a car as the rest of the world? That was something that I thought would be interesting. We could get out of this data set. So what is my parameter of interest here? So I'm trying to say something about I know what the vehicle ownership rate is for Americans, and I want to say something about the rest of the world and how that compares to it. So what I'm interested in saying something about here is a mu, which is the true average rate of vehicle ownership for the world, not including the U.S. Okay. So then, what are my hypotheses here? My null and my alternative hypothesis. So I'm saying something about mu here. So again, think about if this is the question that we want to answer, maybe kind of rephrase it is more helpful. If I want to know, the claim that I'm interested in saying is the rest of the world is at most half as likely to own a car as Americans. So if Americans are twice as likely, then the rest of the world is at most half as likely as Americans. So what value do I want to compare to? If my vehicle ownership in the U.S. here per 1,000 people is about 800. Yeah, so I want to know if this is less than or equal to. So at most, 797 divided by 2. Okay, and my null value, I'll compare this to 398.5. Okay.
Could you also do mu is equal to 87, and the H alternative is greater than or equal to twice that value? Or is that a different question?
Say that again. So could you also do
Mu is equal to 87 over 1,000 proportion, and the H alternative is, or mu is equal to twice that proportion, and then the H alternative would be twice that or equal to that proportion.
So where'd you get the 87? The sample size?
Yeah. So if it's greater than twice that value, is that the same question?
So n is just the number of observations that I have. So I have a number on the vehicle ownership per 1,000 people for 87 countries.
Okay.
So the 87, that doesn't tell me anything about the actual rates that I have going on here. Yeah. So I think the answer is no. But yeah. Okay. So here we can look at the data here. I pulled this up in Jump. Have a histogram here and then some summary statistics there. So I guess the main reason that we look at the data is thinking about sort of what is the distribution of vehicle ownership sort of for the rest of the world. And again, we always want things to be normal, right? Does that look like a normal data set here? Definitely not, right? So we're going to need, well, here you already know what the sample size is. We're going to be okay since our sample size is big enough, but the data is clearly not normal here. But because our sample size is large enough, we can still use these procedures. So can I use the what we talked about in this class? So again, I don't know the population variance, and my population is not normal. But my sample size is 87, which is bigger than 30, so we're okay as far as my sample size goes. So even though I don't have a normal population, because my sample size is large enough, I'm okay here. Again, I also need a random sample. And who knows if I have a random sample? Is the person who submitted this data set in here? I think probably not. So we would want to ask them how they selected these 87 countries. I don't know if there's a random sample. We'll assume for now that the sample is okay, that it's somehow representative of the rest of the world in general. These 86 countries represent the rest of the world here. So we'll assume that we do have a random sample here. Okay, so if we're going to actually do the test, out of interest of time, I'm going to skip ahead here to show you that I can actually do this test just in Jump as well. So we could calculate our test statistic, which would be x bar minus mu 0 over the sample standard deviation over the square root of n. So our sample mean, we can find that's 324.92. Our hypothesized mean was 398.5. Standard deviation was 251.7 over the square root of 86.
You took out the U.S. for this.
I took out the U.S. for this. That's right. Yep. All right. So I'm comparing the rest of the world to the United States. Yeah. And again, because my alternative was that the mean was greater than, or less than or equal to, or less than 398.5, I can pick out my p-value right there. And so, so what am I going to do here? Am I going to fail to reject or reject if my p-value is 0.0041? I'm going to reject the null hypothesis. That's right. And so what does that mean here? That means that based on this data set anyway, there is sufficient evidence to conclude that the rest of the world is half as likely to own a car as the U.S. Okay? Yes, sir.
So this data, it's like done by country, right? So it's not population weighted.
Correct. It's done well. So it's a rate per 1,000. Yeah.
So it's still the population.
So it is population weighted. That's right. Yep. Matt.
What was the country that had the really high number on the bar graph?
That's a good question. What was the country that had the really?
It's San Marino.
Okay, I knew it was some very kind of small, strange country. Yeah. So it was San Marino. I guess was way up here, and that's maybe sort of an outlier that would maybe be good to ignore, I guess. Anyway, so I guess I just wanted to show you how if I have a data set that I'm interested, I can use what we've done in this class to actually answer some of these questions. So I just wanted to kind of bring one of those data sets in to do here as well. Okay, I think we are ready to move on to Chapter 9. And here in Chapter 9, titled, we're doing inference based on two samples. So, newsflash, we're going to be doing exactly the same thing we did in the previous two chapters, hypothesis tests and confidence intervals, but now we're going to do this for two samples, or two populations. So we're getting more complex and I think slightly more interesting here. But in any case, we'll move through this maybe a little faster than we have done already. Okay, so motivating example here. This Consumer Reports article from a long time ago was comparing types of batteries, and the study compared the average lifetime for a Duracell AA battery and an Energizer AA battery. And again, you're comparing these things. You might sort of what you might be interested in is which one lasts longer. So which one has the longer average lifetime. So the question that we might want to know is how can we determine which brand of AA battery lasts longer, sort of overall? What's the average performance of these batteries? So that's kind of the type of question that we'll be going to answer. So instead of just saying something about one population, we'll be doing more comparative between groups. How can we compare these things? Okay, so our assumptions are that we have a random sample. Sort of our first round here, we have a random sample from one population, so from one distribution that has mean mu1 and variance sigma 1 squared. And then we also have a sample from a second population, or a second distribution that has mean mu2 and variance sigma 2 squared. And again, just note that we can have different sample sizes, so we'll use m and n to represent those different sample sizes that we might have. Okay, and very important assumption, we'll also assume that the samples are independent of each other. So that's an important thing we need to assume for this chapter. Okay, so again, if I want to, thinking back to what we did in chapter 7, if I want to estimate mu1, I can use x bar. If I want to estimate mu2, I can use y bar, sample average, or sample mean to estimate the population mean. So the proposition, and this is kind of going back to our what we learned in chapter 5. The expected value of x bar minus y bar is mu1 minus mu2. So we have an unbiased estimator of our difference between means. So again, if I want to estimate mu1 minus mu2, the difference there, the expected value here of x bar minus y bar. Again, remember I can distribute that expectation. I have a linear thing there, so this is the expected value of x bar minus the expected value of y bar. And we know those sample means are unbiased, so this is equal to mu1 minus mu2. And so we're trying to estimate this difference between means. We're trying to estimate mu1 minus mu2, so that means we have an unbiased estimator here, which is good. But then we also want to say what the standard deviation of our estimate here is. So let's look at the variance. The variance of x bar minus y bar. Okay, and so remember that my samples are independent. So I have an independent sample of my x's, an independent sample of my y's. So what that means is that x bar and y bar are independent because the samples are independent. So as random variables, these are independent. So what that means is this is equal to the variance of x bar. And then we have a negative one that we can pull outside and square times the variance of y bar. So we're just going to add up the variances here. And in general, what's the variance of x bar? Going back to chapter 5. Yes. So we want to. So the variance of x bar here. This is the expected value of x bar squared minus the expected value of x bar squared. But how does that relate to the variance of my population? So if the x's have variance sigma squared, what's the variance of x bar? Yes, thank you. So variance of x bar is always the variance of the population divided by its sample size. So sigma squared over n was what that was. So that is correct, but sort of your shortcut there is just the variance of the population over sample size. So the variance of my x's was sigma squared 1, and I had m of those. The variance of my y's was sigma 2 squared, and I had n y. So my sample size for the y's was n. So that the standard deviation of my estimate, standard deviation of x bar minus y bar, is just the square root of that. So sigma 1 squared over m plus sigma 2 squared over n. Okay. So you can kind of maybe see this fitting into the general framework that we've done. If I want to estimate a parameter mu back in chapter 7, I can find an unbiased estimator and figure out what its standard deviation is, and then use that to construct my confidence interval and hypothesis test. Same thing here, just now my parameter of interest is this difference in means, mu1 minus mu2. So my estimate is the difference in sample means, and then I can figure out what its standard deviation is in order to construct my confidence intervals and hypothesis tests. So kind of the same type of strategy that we have done before. So assuming now, first of all, we'll start out in our case 1, where I have if my population is normal, and I know what the variance is, sort of our usual case here. So what's the parameter of interest here? I'm interested in mu1 minus mu2, the difference in population means. Okay. And so my null hypothesis, what we'll use here, is that this difference, mu1 minus mu2, is equal to some value delta 0. So delta 0 will often be 0. So most of the time I'll be seeing if these means are exactly the same, but I could, in more generality, look at if they have some difference between them. And then the alternative is going to be the same as we've seen before here. So it's either either this difference is either greater than delta 0, less than, or not equal to. So I'll still have one of the same three alternative hypotheses that we've had before. It's just kind of translating into this new setting here. Okay, so then I want to observe independent random samples. So I'll observe x1 up to xm that are IID normal mu1 sigma squared 1, and I'll observe random sample of y's to yn from the second population. And I'm saying that sigma 1 squared and sigma 2 squared are known for now. So again, that's sort of unrealistic, and we'll come back to that assumption later. And I'm also so I have normal populations where I know what the variance is. It's kind of a motivating example here. Okay. So since my samples are independent here, and I found what my estimate is going to be x bar minus y bar, right? And I already found what the mean and variance of x bar minus y bar is, and since the populations are normal, their difference is also going to follow a normal distribution. This goes back to chapter 5 again. Remember, the sum or linear combinations of normal random variables are also normal. So this thing is going to have a normal distribution. Its mean is mu1 minus mu2, and its variance is sigma 1 squared over m plus sigma 2 squared over n. Okay, and the test statistic we're going to use, big surprise here, is our estimate minus what we've hypothesized that value to be, and so if the null hypothesis is true, then this is equal to mu1 minus mu2, and so there we've standardized by the right thing, and we have a standard normal random variable. Okay, so very, very similar setup as we've seen before. And so what we'll do, we'll actually calculate what this test statistic is, and note that we have all this information, right? I know what my sample means are. I have my hypothesized difference. I know what my variances are, and I know what my sample sizes are. So this is something that I can calculate. And then finally, of course, I'll make a conclusion. And so we're going to do the same thing we've done before. So compute p-values and conclude. Same as we did for the z-test or the z-interval in chapters 7 and 8. Okay, I guess here we're talking about a test. So we'll compute our p-values and make the conclusions the same way that we did for the z-test back in chapter 8. Okay, well let's do a quick example here. Maybe we'll finish up here, I guess, probably. So going back to our battery example, so again, we're going to assume now that we have normally distributed lifetimes, which that's a questionable assumption, but we'll go with that for now. And we'll say that the standard deviation of the Duracell batteries of our first sample is 1.8. The standard deviation of our Energizer batteries is 2. And we're going to take a random sample of 100 of each of these things and find our sample mean there of 4.1 and 4.5. So is this evidence that the Energizer batteries last longer on average than our Duracell batteries? Okay, so let's just set up our notation here, and we'll let X denote the Duracell sample, and we'll let Y denote the Energizer sample. And so what so the hypotheses that I might want to test here, I want to say something about mu1 minus mu2, and this is mu1 is for X, mu2 is for Y. And then my alternative hypothesis is going to also involve the parameter here, mu1 minus mu2. And now I just need to fill in the hypothesized value and sort of what inequality I'm looking at here. So again, the question that I have is this evidence that the Energizer batteries last longer on average than the Duracell batteries? So what should go in my alternative hypothesis? Less than zero. Nice. Yeah. So my question says that the Energizer or the samples of Y last longer than the samples of X. So that means mu2 would be bigger than mu1. Okay, and then I'll just set mu1 minus mu2 equal to 0. So I'm comparing the average lifetime of these batteries. Okay, and so if you look back at sort of what we require here, we have independent random samples. So that's good. And we also, for this first procedure, we need normal populations and known variances, which we're also assuming that we know. So we're good to go here to do this two-sample z-test. So we can calculate our test statistic. First step is always calculate your test statistic. So we have x bar minus y bar minus delta 0 over the standard deviation, sigma 1 squared over m, sigma 2 squared over n. So what's delta 0 here? 0. That comes from our null hypothesis. So our sample means here we have 4.1 minus 4.5 minus 0. First variance was 1.8. The first standard deviation was 1.8 over 100, and our other variance was 2 squared over 100. And if you calculate this, you'll get a negative 1.49. Okay, so have my test statistic. What's my next step? P-value, absolutely. So my p-value, again, I have a standard normal here, and I want to know something about negative 1.49. What symbol goes in the, what's my probability that I want to find here? Less than. Why do I have a less than? Right. So, so you want to make sure just to match that up with the alternative hypothesis, because I'm looking at a less than, regardless of what my test statistic is. I want to make sure to use that inequality sign. So, the question I might have originally asked was, do I have evidence that Duracell batteries last longer than the Energizer? In which case, I'd want to look at the greater than, even though my test statistic is negative. So, your p-value doesn't always have to be a tail probability. Is a good reminder here, but here it is. So if you look this up in the table, this is 0.0681. Okay. Just wrap this up quick. Our p-value is 0.0681. So what's my decision going to be here? compared to a significance of 0.05, and that's correct. So I didn't tell you what significance level to use. So if you're not told, you can sort of just assume go with alpha equals 0.05. So this is bigger than alpha, which is 0.05. So therefore, I fail to reject. Let's quickly let me get this interpretation down. There is not evidence to conclude that the Energizer batteries last on average. So when we're looking at a average behavior here, longer than Duracell. Okay, so remember our alternative hypothesis said that the Energizer batteries do last longer, and here we say we don't have evidence for that. So there is not evidence to conclude that is true. Okay, sorry for keeping you guys over a minute. I do have your homework 6 if you want to come grab that. Otherwise, have an awesome weekend. There you go. Good about having an extreme name, right?
Yeah. Better than wait the longest.
Better than my M.
Oh yeah, you got to dig.
Oh,
dig.
look at that. Bingo.
Must be a Friday.
Running good.